Hey everyone, welcome back to the channel. In this masterclass we are doing a complete, from the ground up deep dive into variables, scope and lifetime. By the end of this video you'll understand it well enough to use it confidently in production and explain it clearly in an interview. If that sounds good, make sure you are subscribed and let's get started. Every Java program is a story of variables appearing, doing their job, and disappearing. This section builds a precise mental model of the three kinds of variables that matter most: local, instance, and static, covering their memory location, their lifetime, and what the JVM does when you forget to initialize them. These are the mechanics that separate developers who guess from developers who know. Java has exactly three categories of variable that every developer must master. A local variable is created when execution enters a method and destroyed when it leaves. An instance variable is born with an object and dies with it. A static variable is tied to the class loader and can outlive every object ever created from that class. Getting these categories wrong is the root cause of a surprisingly large number of production bugs. Quick pause: if this is useful so far, drop a like, subscribe for a new masterclass every week, and share it with a teammate who would find it useful. Now, back to it. The JVM carves memory into distinct regions. Local variables live on the thread stack, fast, automatically reclaimed when the method returns. Instance variables live on the heap, allocated when an object is constructed and garbage collected when no references remain. Static variables live in metaspace, which is managed by the class loader rather than the garbage collector. Understanding which region a variable occupies tells you immediately how long it can survive and who is responsible for cleaning it up. A local variable is scoped to the block that declares it. The variable steps lives for the entire method body, but tick is recreated on every loop iteration and ceases to exist the moment execution leaves the while block. Trying to reference tick outside that block is a compile time error, not a runtime surprise. This is the compiler enforcing lifetime rules on your behalf, and it is one of Java's safest features. Request count is an instance variable. Every session object gets its own copy, so two sessions counting requests never interfere with each other. Total sessions is static. There is exactly one copy in memory regardless of how many session objects exist. When the static counter increments inside the constructor, every object shares that same change. Confusing these two is a classic source of test pollution, where a static counter carries state from one test into the next. The JVM guarantees that instance and static variables are given a predictable default value at the moment memory is allocated: 0 for numbers, false for booleans, and null for object references. Local variables receive no such guarantee. The compiler demands you assign a value before you read one. This asymmetry is intentional. The JVM cannot enforce initialization order for fields the way the compiler can for locals, so it falls back to 0 in memory instead. The practical rule of thumb is to give a variable the smallest scope that satisfies its purpose. A local variable that is visible for only 3 lines of code cannot leak, cannot be mutated by another thread, and cannot carry stale state between test runs. When you genuinely need shared state across objects, reach for a static variable consciously, knowing it lives in metaspace, knowing it persists for the lifetime of the class loader, and knowing it requires synchronization in a concurrent context. We start with precision. Not the textbook hand wave, but the exact way the Java language specification defines variables, categories, and the rules the compiler enforces before your program ever runs. Every topic in this section builds directly on that foundation. The JLS defines a variable as a named storage location that holds a value of a specific type. Each word carries weight. It is named because you refer to it by an identifier. It is a storage location because it physically occupies memory while the program runs. It is not an abstraction. And it has a specific type because Java is statically typed. The compiler resolves that type before execution, even when you use the var keyword introduced in Java 10. Var infers the type, it does not remove it. The JLS recognizes exactly 4 categories of variables: local variables, instance variables, class variables, also called static variables, and array components. This masterclass goes deep on the first 3. Array components share important initialization and lifetime behaviors with instance and static variables, so we will call them out at the relevant moments. Local variables are the workhorses of everyday Java code. They exist inside a method, a constructor, an initializer block, or a lambda body solely to help that piece of logic do its job. The single most important fact to internalize right now is this: the JVM does not give local variables a default value, and the compiler enforces that you write to 1 before you read from it. The compiler sees that X was declared but never assigned a value before being read, and it refuses to produce bytecode. This is the definite assignment rule in action. It is a feature, not a limitation. It prevents you from reading bytes that may contain garbage from whatever was in that memory location previously. Both forms satisfy definite assignment. Separating declaration from initialization is legal as long as the compiler can prove every possible code path assigns a value before a read. In practice, the idiomatic form is to declare and initialize on the same line. Declare, initialize, use, that is the pattern to default to. Scope defines the region of code where a variable can legally be referenced by name. For a local variable, scope opens at the point of declaration and closes at the matching closing brace of the enclosing block. The variable y lives and dies inside the if block. Past that closing brace, the compiler does not recognize the name at all, not just the value. This is Java enforcing clean architecture at the language level. Keep the scope of every variable as small as possible, and the compiler will hold you to it. When a method is invoked, the JVM creates a stack frame for it. Local variables live inside that frame. A variable enters scope at its declaration, becomes usable after initialization, and leaves scope at the closing brace of its block. When the method returns, the entire stack frame is destroyed, reclaiming all the memory those local variables occupied. This is why local variable lifetime is tightly bounded, and why the scope as small as possible principle is not just style advice but a reflection of how the JVM actually manages memory. This section covers 3 closely related features of local variables in Java. We start with the final keyword, move into the subtler concept of effectively final variables, and finish with var, the type inference keyword introduced in Java 10. Declaring a local variable final tells the compiler this slot may only be assigned once. Any attempt to reassign it, even to the same value, is a compile time error. Think of it as a contract. The value is set once and stays that way for the life of the method call. A variable is effectively final when it is never reassigned, even though the final keyword is absent. The compiler enforces this rule automatically. This concept became critical in Java 8 because lambdas must capture local variables that are either explicitly final or effectively final. Here threshold is never reassigned, so the lambda can capture it. The moment you add a reassignment anywhere in the method, the compiler rejects the lambda. Adding a single line like threshold equals 200 breaks the contract, because threshold is no longer effectively final. A lambda may outlive the method that created it. When the method returns, its stack frame is gone, but the lambda object lives on the heap. Java solves this by requiring the compiler to capture the value at the moment of creation, not a live reference to the stack slot. Immutability guarantees that captured value never changes, so the lambda always sees a consistent, valid snapshot. The var keyword tells the compiler to reduce the type from the right-hand side of the assignment. The type is still resolved at compile time. This is not dynamic typing. Omitting an initializer is illegal because the compiler has nothing to infer from, and once the type is inferred, it is fixed for that variable's lifetime. Var is strictly a local variable feature. It cannot appear as an instance variable, a static field, a method parameter, or a return type. Whether to adopt it is a team-style decision, but understanding what it is, compile time inference, not dynamic typing, is essential before making that call. We've established what local variables are. Now we go one level deeper, into the JVM itself, to see exactly where they live and what happens to them when a method is called and returns. This is where your understanding genuinely separates from the majority of Java developers. Every time a thread calls a method, the JVM pushes a brand new stack frame onto that thread's private call stack. The most recently called method sits at the top. When a method returns, its frame is popped and destroyed. Each frame is a completely self-contained unit of execution. Methods cannot reach into each other's frames. A stack frame has three main parts. The local variable table is the array where your named variables physically live as numbered slot positions, not names. The operand stack is the JVM's scratchpad for arithmetic and instruction results. The constant pool reference links the frame back to class-level data like string literals. The most profound detail, in any instance method, slot 0 is silently occupied by this. You've used this for years, it is literally just the first local variable slot. Here is a minimal instance method, 3 local variables, 1 addition, no return value. This is the source we will trace directly into JVM bytecode so you can see exactly how each variable maps to a slot in the local variable table. The Java compiler erases variable names entirely. A, B, and C become slot 1, slot 2, and slot 3. Slot 0 is occupied by this, which is why the numbering starts at 1. The operand stack ferries values between instructions, and when return executes, the entire frame, every slot, every value, is gone from memory immediately. The compiler is free to reuse an LVT slot once a variable goes out of scope. But it is not required to do so immediately. In certain JIT compilation scenarios, the slot can still hold the old reference even though the language says the variable is gone, and as long as that reference exists, the garbage collector cannot reclaim the object. In a long-running method, that can mean megabytes sitting in memory far longer than intended. The fix is straightforward: assign null to the variable before the long-running work begins. This writes null into the LVT slot, severing the reference and making the object eligible for collection. You do not need this in everyday code, the JIT handles most cases correctly. But in memory-sensitive batch jobs, event loops, or any method that holds large allocations and then does prolonged work, this explicit nullification can prevent subtle, hard-to-diagnose memory pressure. We shift focus from the stack to the heap. Instance variables give every object its own independent state, while static variables are shared across an entire class. Understanding how the JVM allocates zeros and eventually collects this memory is essential for writing correct, predictable Java. Instance variables are declared inside the class body, outside any method, without the static keyword. Unlike local variables, they do not require an explicit initializer. The JVM assigns default values automatically. An int defaults to 0, an object reference defaults to null. This is guaranteed by the specification, not optional behavior. PageViews.co and ClickEvents.co are entirely separate storage locations sitting in separate objects on the heap. Incrementing one has zero effect on the other. This per-object isolation is the defining characteristic of instance variables, and it is what makes object-oriented encapsulation possible. When new is called, the JVM performs 4 steps in strict order. Memory is allocated on the heap. That entire region is bulk zeroed before any Java code runs, instance initializes execute in textual order, and finally the constructor body runs. The zeroing step is why every instance variable already holds its default value by the time your constructor's first line executes. Every object on the heap begins with a header. The mark word tracks garbage collection state, monitor lock information, and the identity hash code. The class pointer links this object to its class metadata in the metaspace. Field data follows immediately after, and the JVM inserts alignment padding as needed to keep fields on their natural boundaries. Instance variable lifetime is object scoped. The data lives exactly as long as the object that contains it. Reachability is determined by whether any path of references connects a GC route to the object. The moment that path disappears, the object is eligible for collection, and all of its instance variables are reclaimed with it. Static variables are the most architecturally significant variable type in Java. The Java language specification calls them class variables because there is exactly one copy per class, regardless of how many instances exist. That single copy lives in the metaspace alongside the class metadata, not inside any object on the heap. Max_retries is a static final field initialized with a compile time constant literal. The compiler inlines the value 3 directly into every bytecode call site, so no memory read is needed at runtime. Instance count is a mutable class variable, one shared slot updated across all instances. The logger field is static and final but not a compile time constant. Because its value is computed at runtime, it is not inlined, and binary compatibility rules differ from those of true constants. Let's recap the key takeaways from this masterclass. If this helped you, hit the like button, subscribe for a new deep dive masterclass every week, and forward this to a teammate who would find it useful. Drop your questions in the comments, I read every one. See you in the next one.